Hi students, welcome to the class of Design and Analysis of Algorithms Lab. This is the 5th semester subject of Computer Science and Engineering Diploma. Today I am going to deal with the session 1, that is the QUICKSORT. Myself Reshma Attawar and I am the facilitator for this particular subject. The session objective is writing QUICKSORT program using the divide and conquer techniques. And the session outcome is you will be able to understand QUICKSORT technique, write the program using the learned QUICKSORT technique. So the exercise 1 is sort a given set of elements using the QUICKSORT method and determine the time required to sort the elements. Repeat the experiment for different values of n. So first we should know what is QUICKSORT. QUICKSORT is a divide and conquer algorithm. It is also called as partition and exchange algorithm. Okay, mainly what happens in QUICKSORT? It picks an element as pivot and partitions the given array into the picked pivot. That is, if you have a pivot, like if you have an element called as pivot, then it partitions the array based on the picked pivot. So now we can pick the pivot in different ways. Either you can pick the first element as pivot, you can pick the last element as pivot, pick a random element as pivot, or pick a median as pivot. So depending on your way of writing the program, you can pick any element as a pivot element. So first let us see how the QUICKSORT works. Consider an array A of I where I is ranging from 0 to n-1. As we all know that array elements will start with the index 0 and ends with the n-1 elements where n is the size of the array. Okay. So we can formalize the division of array elements as A of 0 to A of m-1, then A of m, then comes A of m plus 1 and then the A of n-1. So this is how the array elements are present. And these elements are not sorted, it's an unsorted array. So what is the meaning of sorted or unsorted? Sorted means arranging the array elements in a particular order. It can be an ascending order or it can be in a descending order. Okay, the main purpose of QUICKSORT is it is a method of sorting the array elements in a particular order. Okay, in our case we are going to arrange the elements in the ascending order. Now first we will see which element is taken as pivot. So in this example we are taking A of m as pivot. So if we select this particular element as pivot, then all the elements that belong to the left subarray are smaller than pivot element, and all the elements that belong to the right subarray are greater than pivot element. So here you can see that elements are greater than pivot, and here you can see that the elements are lesser than pivot. So this is the main concept for QUICKSORT, or the base for the QUICKSORT. Selecting the pivot is the base for the QUICKSORT algorithm. Now diagrammatically we can show that if this particular element is taken as pivot, then all the elements that are to the left side of the pivot element are less than pivot. Then we can consider these elements are the left subarray, and all the elements that are belong to the right side of the pivot element are greater than pivot element. So in this way we are going to partition the array into two subparts. Okay. So let us take an example for the QUICKSORT. Before taking one example, first we should know on what basis the QUICKSORT work. What are the different steps we follow in order to perform the QUICKSORT operation. So if you select, let us say this is a set of array elements and the name of the array is A. Okay, and the elements in the array are 50, 30, 10, 90, 80, 20, 40 and 70. So array elements are not arranged and they are unsorted, or they are not ordered properly. So we are going to use some variables like low, high, I, pivot and j. So these are the different variables we are going to use. Now what is the purpose of using low? Low is used to point to the beginning of the array. So in order to access the beginning of the array element, we are going to use a variable called as low. We are going to use one more variable called as high, which is going to access the end of the array. It is going to point to the end of the array. Therefore, we are going to use two more variables I and j, where I is going to point to the beginning of the array and it keeps on moving, and j is going to point to the end of the array. So it acts as an index to the end of the array. And one more variable called as pivot. So in our case, we have taken the first element as pivot. Okay, we can select any element as pivot. We can either select the middle element, or you can select the last element, or you can select any random element as a pivot element. It is left to you. But in our example, we are taking the first element as a pivot element. So a of pivot will always fetch you 50. We will now split the array into two parts. Now how the splitting will take place? The splitting will take place based on the partition you are going to make. How the partition takes place? The partition will take place based on the element you have selected as a pivot element, right? Now we'll see how the partitions takes place. So partition will have the following set of operations which is performed continuously again and again until some condition is true or false. Now the first operation that performed is start incrementing I until a of I is less than a of pivot. So what they are saying here is you have to keep on incrementing the I variable in such a way that the whatever value fetched by a of I, it should be always less than the pivot value. Okay, so here you can see 30 is less than 50, so keep on incrementing I. Now I will point here. So in this way it continues. Got it? Now stop incrementing I as soon as a of I is greater than pivot, a of pivot. That is, we can see that as soon as the element pointed by the I. Okay, so the element that is fetched by I, that is in our case it is 90. So if 90 is greater than 50, you have to stop incrementing I. Now we have to come to j. Okay. Now we have to come to j. Now start decrementing j. So when you are decrementing j, until when the element pointed by j is greater than the pivot element. So in our case 70 is greater than 50. So it will start decrementing j, that is j minus minus. Till where you have to do? Stop decrementing j when a of j is less than a of pivot. So as soon as you can see here 40 is less than 50. So now you have to stop decrementing j. Once you stop decrementing j, once you stop decrementing I, now check the position of I and j. If I is less than j, that the position of I is less than position of j, then you have to swap a of I with a of j. Okay. And if the j has crossed I, suppose it keeps on incrementing until the decrementing until the elements pointed by j is greater than pivot. So as soon as it crosses I, if I is somewhere here and if j is somewhere here, in that case what you have to do? You have to swap the jth element with the pivot element. Okay, so that is the procedure for the partitioning. So this has to be done continuously until you get the pivot element is located in its proper position. Okay, now let us see the example to make these points more clearer. Okay, in the step 1, what happens is we can see that this is the initial way all the variables are pointing to. So low is going to fetch the first element, high is going to fetch the last element of the array, and I is pointing to the first element, and pivot is also pointing to the first element, and j is pointing to the last element. This is the initial way representation of the quicksort before it gets started. Now let's select the first element as pivot. So a of pivot is how much? 50. The second step. In the second step you can see that we are going to increment I. So increment I. Now I is pointing to 30. Now check whether a of I is less than pivot. Yes, it's true. A of I is less than or equal to a of pivot. That is 30 is less than 50. Now continue to increment I. Now you have to once again increment I. Now I will come here I plus plus, so I will come to this particular place, right? Until the element pointed by I is greater than A of pivot. So now A of I is how much? 10. So now 10 is less than 50, right? So now keep incrementing I as A of I, that is 10, is less than A of pivot, right? So now I will become I plus plus, now I will point to 90. Now what happens? So here you can see that once again 90 is greater than 50. Now the condition is false. That is A of I is greater than A of low or A of pivot. That is 90 is greater than 50. Now what you have to do? You should not increment I. You have to stop incrementing I. So I will stop here and start with J. Now let us come to J. So you can see here the element pointed by J, that is 70, is greater than 50. So when the jth element is greater than the pivot element, you have to keep on decrementing I. So J minus minus, so now J is pointing to 40, right? So now J is pointing to 40. Now decrement J, because now 40 is there. A of J is greater than pivot, A of pivot, right? Now what happens? So you can see here 40 and 50, we can see that 40 is less than 50, so stop decrementing J, because 40 is less than 50. Only when the element pointed by J is greater than the pivot element, you have to keep on decrementing J. But in our case, what happened is 40 is less than the pivot element. Now we have to stop decrementing J and you have to check the position of I and J. We can see here that I is less than J. Why I is less than J? Because ith position is how much? 0, 1, 2, 3. I is in the third position and J is in the sixth position. So automatically 3 is less than 6, right? 3 is less than 6. So what we have to do? We have to swap A of I with A of J. Okay, that is the procedure. So once you swap, what happens? 40 will come and sit in the ith position and 90 will come and sit in the jth position. Now once again perform the same operation. Now come back to I. Now check whether the A of I is less than A of A of pivot, that is 50. Yes, 40 is less than 50. Now start incrementing I. Once again do the same procedure. Now I is pointing to 80. Now check A of I with pivot. So A of I is 80 and A of pivot is 50. Now we can see that 80 is greater than 50. So what we have to do? We have to stop incrementing I. Okay. So after stop incrementing I, stop it here and come back to J. Now what you have to do? Start decrementing J. Now J is how much? 90. Now 90 is greater than 50, so start decrementing J. J will come and point to 20 until the jth value is greater than pivot value. Right, now what happens? 20. 20 is less than 50, now stop decrementing J. Right, now J will be decremented, J will not get decremented because 20 is less than 50. Okay, that is 20 is less than 50. Now what you have to do? Now after stop decrementing J and stop decrementing I, now you check the position of I and J. So I is smaller than J. Yes, I is smaller than J. Then you have to swap A of I with A of J. So now 20 will come here and 80 will go here. 20 will be here and 80 will go here. Right, that is swap 20 with 80. Okay, now 20 is here and 80 is here. Now once again perform the same operation, that is check whether A of I is less than pivot. Yes, A of I is less than pivot, so come here, I and J is pointing to 80. Now check the I. Yes, A of I is 80, which is greater than 50, so stop decrementing I. Start decrementing J. Yes, 80 is greater than 50, so J will come here. Right, so this will happen. So now J has crossed I. You can see here J has crossed I. Right, so once the J has crossed I, what we have to do is we have to swap A of J with the pivot value. because j will cross only when it finds a small element. Okay, so when 20 a of j is less than a of pivot, then you have to swap a of pivot with a of j because j has crossed I. So you can see here, as a of j is less than a of pivot and j has crossed I, that is j is greater than I, swap a of pivot with a of j. Hope it is clear. So this till here the first pass will become, so this is the first pass where we can say that the pivot has been exchanged with the j or swapped with the j. So this is the exact position where the pivot has to stay. So 50 is the exact position where that particular element has to stay. Now you can clearly observe that all the elements in the left subarray are smaller than the pivot value, and all the elements that are greater to the right subarray of that pivot are the elements that are greater than pivot. Okay, so pivot is shifted to its exact position. So this is a position where pivot has been shifted, and we can now onwards we should not touch this position because this is the exact position where that particular element has to sit. Right, now we have to do the same procedure for the left subarray. Right, so now start sorting the left subarray. So once you complete the sorting the left subarray, start with the right subarray. Don't go to touch the pivot. So here consider the first element as the pivot element. So here we have to consider 20 as the pivot element. Right, okay, now 20 is the pivot element. We can see here, set I and j pointer. So I is set here and j is set here. So when you set I here, you have to check that 30 is less than 20. No, so don't stop incrementing I. Don't go to increment I. Okay, now start with j. Whether 40 is greater than 20? Yes. Now j will come here. Right. So we can see here, as a of I that is greater than a of pivot, then stop incrementing I and start decrementing j. Okay, now j will become j minus minus, so j will point to 10. As a of j is less than a of pivot, we can see here that a of j is less than a of pivot, that is 10 is less than 20. So you have to stop decrementing j also. Now what you have to do, check the I is less than j. Yes, I is less than j. So now what you have to do, if I is less than j, then you have to swap 30 with 10. Right. So swap 30 with 10. So 10 will come here and 30 will go here. Okay. Now once again perform the same operation. Now check whether a of I is less than pivot. Yes, it is less than pivot. Now what you have to do? Start incrementing I. Okay. So start incrementing I. So I will point to 30. Okay. So increment I. So I is pointing to 30. So I and j both are pointing to 30. Now check the position of I. So I is pointing to 30. So 30 is less than 20. No, 30 is greater than 20. So stop incrementing I. Now start with j. So a of j is 30. So 30 is greater than 20. So start decrementing j. So decrement j. So j will point here. Now you check whether a of j is greater than a of pivot. No, a of j is less than a of pivot. So stop decrementing j. But what we can see here is j has crossed I. So once j has crossed I, what you have to do? You have to swap a of j with the pivot value. So swap 20 and 10. So 20 will come here and 10 will come here. So this is the exact position of the pivot. So 20 should always remain here. This is the exact position where 20 has to reside. Now all the left sub-elements you can see they are smaller than 20, and all the right subarray, that is 30 and 40, are greater than 20. Only one element is left in the left subarray, so we can keep it as it is. Now we'll go to the right, sorting the right one. Okay, so you have to sort the right subarray, which is already sorted. So it is already sorted. Now we can see the entire left subarray is sorted. Now we will go to the right subarray. As left subarray is completely sorted, sort the right sublist. Okay, assume that the first element of the right one as a pivot. Now we have to assume 80 as the pivot element. Now perform the same operation again repeatedly or recursively. So you can see here pivot 80 is pivot and I and j is here. Now check the a of I with 80. Yes, a of I is greater than 80. So stop incrementing I. Now let us start with j. You can see 70 is less than 80. Stop decrementing j. Okay, now what you have to do? In this case, you can see that I is less than j. So you have to exchange or swap a of I with a of j. Okay, swap a of I with a of j. So 70 will come here and 90 will go there. Once again perform the same operation. Check whether a of I is less than pivot. Yes, a of I is less than pivot. So increment I will point to 90. So both I and j is pointing to 90. Now check a of I with is less than 80. That is pivot value. No. So stop incrementing I. Now go to j. Check whether a of j is greater than 80. Yes. Now j, decrement j. So now j is pointing to 70. Now check that a of j is greater than 80. No. So stop decrementing j. And but j has crossed I, we have to swap pivot with the a of j. Hope till now it's I think very clear for you to know the concept of the quicksort. Now we can see that pivot has been given its exact position, and we can see that the left subarray, that is 70 and 90, are properly sorted. So we cannot divide it further, and all the array elements are sorted neatly. So this is the final sorted array you will get at the end of the quicksort program. Got it? So this is the logic behind solving the quicksort. Now let us see the algorithm for quicksort. So algorithm quick, first you have to write the algorithm keyword and then write quick and then check the number of parameters. Pass the parameters. So we have to pass a of 0 to n minus 1, that is the array elements, then pass the low and high. Low is going to give the first element of the array and high is going to give the last element of the array. Problem description is to perform the sorting of array elements a of 0 to n minus 1. What is the input given? The input is the unsorted array a of 0 to n minus 1 and the output is the sorted array a of 0 to n minus 1. Okay, now we will go to the exact steps. So in the quick is because if the quick is called recursively, we have to use the recursion method here. Before that, we have to check if low is less than high. We have seen in the program example also, we have to check whether the low is less than high. Only if low is less than high, then we have to calculate the m. So m is given by partition of a of low to high. We have to call one more function called as partition. Okay. So then once the partition function is called, it will give the exact position of the pivot where m has to reside. So m is the position of the pivot. Okay. So then you have to start sorting the left subarray and the right subarray with the help of the pivot position where the pivot is exactly placed. Okay. So for that we have to go to quick a of low to m minus 1. That is the elements lesser than pivot is the left subarray and all the elements greater than pivot, that is m plus 1 to high, as the right subarray. So this is the quicksort algorithm. Now we will go for the partition algorithm. So in partition we are going to pass three parameters a of 0 to n minus 1, then we are going to pass low and then high. Problem description is, this partitions the subarray using first element as the pivot element. Input is subarray a of a with the low as the leftmost index and high as the rightmost index. Output is partition of array A is done and the pivot occupies proper position and the rightmost index is returned. This is the output what we get. Initially, we have to perform the following initialization. So first one is pivot. So pivot, I told you already, pivot should always point to the first element, that is A of low. We have two more indices I and j, where I is going to take the value of low because low is pointing to the first element and j is going to point to the high plus 1, that is the last element. Right. Now while I is less than or equal to j, you have to perform the following operations repeatedly. What operations you have to perform is, first you have to check whether a of I is less than pivot. I told you until a of I is less than pivot, you have to keep on incrementing I. That's why we have used a while loop. You have to perform the operation continuously. While a of j is greater than or equal to pivot, you have to perform the same operation continuously. keep on decrementing the j. Okay, when when if I is not less than or equal to j, that is ith position is less than jth position, then you have to swap a of I with a of j. When the j crosses I, that is if this is not true, okay, then we have to swap a of low with a of j, that is a of pivot with a of j also we can write here. Then you return the jth position. So j, so what is j? J is the position where the pivot is residing exactly. So now what happens is all the elements to the left subarray will be usually um, less than the pivot, and all the elements to the right of the pivot will be greater than pivot once this partition is done. So looking at that algorithm till now, it's more clearer for you when if you write the algorithm in the stepwise. You can write in this way also. So we know that quicksort is also called as a divide and conquer algorithm, and the steps involved in the quicksort is first you have to pick an element from an array, and this particular element which you have picked is called as a pivot element. Second step is to divide the unsorted array of elements into two subarrays. You have to divide in such a way that all the elements that to the left of the pivot are smaller than pivot, and all the elements to the right of the pivot are greater than pivot. And this particular step is called as the partition operation. Okay. So recursively repeat the step 2 until you get the left subarray with smaller values and separately to the subarray of the elements with the greater values until there are only one element present in the array. Until then you have to keep on doing the operation step 2. Within the same logic we have implemented the C program. Let us see that program. So this is the C program for the quicksort. Okay, so this program is more clearer if you write the program and execute, it will be more clearer for you, but briefly I am going to explain once again. So we have here two include operations. One is standard IO.h, which is used to include all the input and output statements, and time.h is used to calculate the time required for executing this particular quicksort program. So first we have the function called as void quicksort int number of 25 int low int high. So three parameters are used here. Low and high is used to access the first and the last element of the array. Then we are going to declare variables like I, j, pivot and temp. If low is less than high, that is we have to check every time. Okay, then we have to point, we are taking the first element as a pivot element, so pivot equal to low, then I equal to low and j equal to high. We are making I to point to the first element and j to point to the last element. Now we have to check continuously while I is less than j, we have to perform these operations I plus plus and increment I until the ith position is less than the pivot value. We know that while number of j is greater than number of pivot, that is number is the array name. Okay, decrement j until the value in the jth position is greater than the pivot. So j minus minus. You have to perform the swap operation. When you have to swap? You have to swap only if the ith position is less than the jth position. If j crosses I, then you have to swap the pivot with the a of number of j, or else we have to swap the number of I with the number of j, where number is the array name. Okay, so once you have performed, this is the entire partition operation we have put here. So once you have done till here, you will get the exact pivot value where the pivot position is residing. So based on that, we have to once again call the quicksort repeatedly. Quicksort number low j minus 1, where j is the exact pivot position and j minus 1 is the left subarray. Okay, quicksort number j plus 1 high, this is the right subarray. We are not going to touch the pivot value jth value because j is already in the sorted in its exact position. Okay, so this will be called again recursively and again until the elements present in the array is 1. This is the main function where you are going to call the quicksort function which you have seen just now. So here we have declared the variables I, count, number of 25, and we also have clock underscore t start end. So clock underscore t is one more data type which is going to have two variables called as start and end. We have one more variable called as t, which is of data type float. Now we have to start the clock because we are going to start the quicksort operation. First you have to fetch the array elements. So before that we have to get the count, that is number of array elements you are going to enter. So that is going to fetch into a variable called as count, and then you have to fetch the array elements one by one. For that we are going to use the for loop. So once the array elements are fetched to the number of I, that is number is our array name, then we have to use the quicksort number 0 count minus 1, where number is the array name, 0 is the starting element of the array, and count minus 1 is the end position of the array. So once quicksort function is called, your quicksort operation will be completed. So you have to stop the clock. That's why end equal to clock. Okay. So once the clock will give you the exact timings that is taken for execution of the quicksort program. So after that you have to print the ordered elements. So already the elements are sorted in a particular ascending order. So you can print the elements by using the for loop. For I equal to 0, I less than count I plus plus. We have to print the elements one by one. So finally you have to calculate the time taken for the sorting. So t equal to n minus start by clock underscore t, which is a constant value. Okay, now we have to print the value. The time taken is percentage of t. So this is how the quicksort program works. So there is an output here. I'll give you the more detailed approach while we are demonstrating the quicksort program. Now let us start the Turbo C++ compiler. Okay, so this is the compiler. File new. Now let us write the header files. Hash include stdio.h. We have one more header file, hash include time.h. Okay, so after writing this, so hash include stdio.h is included for including the standard input output statements, and time.h in order to calculate the time taken for executing the quicksort. Now let us write the function void quicksort is a function name, and let us have an array name int number of 25 or 20. So whatever is feasible for you, you can give it. Int first to point and int last. So this will give the first and last element of the array. Okay, you can give it as int low and int high also. Int I, j, which are used as the indices for pointing to the first and last element, and we also want pivot, which is an important thing in case of quicksort, pivot element. Now let us put the condition. If first is less than last, that is until first is less than last, what we have to do? We have to make pivot to point to the first element, and then we have to make I to point to the first element and j to point to the last element. Okay, then we have to use a while loop. So while is used to check whether I is less than j. Until I is less than j, you have to perform these operations continuously, while number of, that is array name number of I is less than or equal to number of pivot, that is it should always be less than pivot as well as, and I should always be less than last element. Okay, so until then we have to keep on incrementing I. We should have one more while loop for checking whether number of j should be greater than number of pivot. Okay, so until the number of j is greater than pivot, we have to keep on decrementing j. We have seen in the example already. So after doing all these, once again you have to check if I is less than j, that is I should not pass j. If I is less than j, then we have to, what we have to do? Tell me student, we have to swap a of I with, number of I with number of j. So we have to use one temporary variable called as temp, and just this is nothing but the swapping operation. Number of I is equal to number of j. Number of j is equal to 10. Okay, so this is over. Now, in case our j has cross type, so we have to write this outside the while loop. In case j has cross type, then we have to swap number of j with the pivot, right? So temp equal to number of pivot. Temp is a temporary variable which is used only for the swapping purpose. Number of pivot equal to number of j. Number of j equal to temp. So after doing this, we have to call the quicksort function repeatedly, right? So quicksort recursively. Number, now when you pass, we know that number of j is in its exact position. That's why you have to pass, the number is the array, and then you have to pass the first element of the array and then the j minus 1 elements, because j element is in its exact position. Quicksort number comma j plus 1 and the last element. So these two are the subarrays. This is the left subarray and this one, second one, is the right subarray. So this will be done continuously. Now let us close the function. Let us go close the if, and then let us close the function braces. So hope our braces are completely closed. So if is closed here and the function braces is closed here. Now let us write the main function. Void main. Void main you will write only when the main function does not return any value. Int I is the index, count is to count the number of elements, and number is the array name. So let us declare the array size as 20. Now let us use clock underscore t to count the time taken for execution. Start and end are the different variables. Next we have float t. Then let us start the clock. Start equal to clock. Now let us print the how many elements you want to enter. Okay, how many elements you want to give, or any statement you can put. Now we have to scan the number of count of elements. So let us scan it to %t ampersand count. So after getting the count, let us fetch one by one array elements. So enter %t elements count. Scanf. No, before that we have to put a for loop, because we have to scan the elements one by one. So for I equal to 0, I less than count, because array always start with 0. I plus plus scanf %t ampersand number of I. So I is the index to fetch the elements one by one. Now let us call the quicksort. So we are calling the quicksort function and we are passing the parameters like number is the array, starting element of the array, and the ending index of the starting index of the array and ending index of the array we are passing. So quicksort will complete the entire quicksort operation. Now let us end the quicksort clock. So end the clock. Now our elements are sorted, so let us print the elements. Printf sorted array. Okay, for I equal to 0 we have to print one by one, right? That's why I equal to 0, I less than count, I plus plus. Printf %d number of I. We are going to print the sorted elements one by one. Now let us fetch the time taken. So t equal to end minus start by CLK underscore tick, which is the constant value. Now print the time taken. Taken is %f t. So this is the main function. So our program is ready. Now let us save the program. So let us save it. What name shall we give? We'll save it as quicksort.c. Okay. Now let us run the program. How many elements you want to enter? So I'll give 6 elements. Enter the 6 elements: 45, 12, 56, 38, 79, 9. Oh, I forgot to give get ch. So if you want to see the output, I have to. Oh, I'll give the get ch. 1 second. So that it will not exit the output screen. It will read one character and stop there. So let us go back to the screen. How many elements you want to enter? Okay, I forgot to give the space also. So I have to give the space now. 5 elements. Enter 5 elements: 12, 23, 10, 6, and one more element 4. Sorted array is 4, 6, 10, 12, 23. But I have not given the space, so let me give some space. Okay, now let us run the program once again. How many elements you want to enter? 5 elements. Enter the 5 elements: 89, 45, 34, 3, 4, sorry, and 2. So the sorted array is 2, 3, 4, 45 and 89. The time taken is 15. Okay, some more spaces all I should give to make it more clearer, and I did not give CLR SCR to clean the screen. Okay, so this is how you can execute the quicksort program. You can execute the same program using dev C++. It is easy to execute here also. You should just type the program as it is, or you can open the program which you have typed already. I have opened it already. Just go to execute, compile and run. So it runs the program. How many elements you want to enter? 4. Enter 4 elements. You can give the elements here, 45 and 34. So order of the sorted element is 34, 45, 56 and 78. The time taken is 11. So the time taken depends on the CPU speed also. Okay, so this is how the quicksort program can be executed using the dev C++. I think the demonstration is clear. Now let us go to the analysis of the quicksort time complexity. So this is the analysis of the quicksort time complexity. We are going to analyze both the time complexities as well as the space complexity. First, let us see the worst case running time. We all know that the quicksort is executed based on the recursive operation. So each time the program, the size we are going to pass here is n. So first time when you pass, the subproblem size will be n. Next time when you pass, it will be n minus 1. So how did you get this here? Left subarray is 0 and the right subarray is n minus 1. The worst case running time, when the quicksort always has the most unbalanced partitions possible. So whenever the quicksort is having the unbalanced partition, that is the partition is not getting exactly at the middle or in the median, then we can say it as a worst case. So worst case mainly occurs when you have a sorted array. Already when you give a sorted array to the quicksort, what happens is the pivot will be the smallest element, right? So when the pivot is the smallest element, there will not be a single element to the left side of the pivot. When you partition it based on the pivot element, the left subarray will be usually 0. Okay, so the worst case will happen only when you select the pivot as the smallest element. Okay, so in this case what happens is the entire partitioning will be unbalanced. Then the original call takes cn time for some constant c. So where c is some constant, we can say some small operations, we will consider it as a c, that is a constant which is not going to change, and n is the time taken, total partitioning time for all the subproblems of this size. So initially our array size is n and the pivot taken is in such a way that we have considered the smallest element as pivot, because of which the left subarray is always 0. Now if you consider only the right subarray, pivot element is cancelled, so because it stays in its exact position, we have to take only the right subarray. So n minus 1 times will be the second subtree. Here it will be cn minus 1, the time taken. Next, once again, if you try to partition this into two subarrays, the left subarray will once again be 0 and the right subarray will be n minus 2. So this will continue till where? Till the element is 1. Array size element is 1. So you can see in all these, in the tree, in this particular tree, the left subarray is always 0. The main reason for the 0 is the partitioning is not done exactly into two divisions, which is because the pivot element selected is the smallest element. So for this, if you count the recursive call time taken, then we can say it as n minus 1 takes for c into n minus 1 time. The recursive call of n minus 2 takes c into n minus 2. So this will continue as it is till the size of the array becomes 1. Okay, so now worst case running time, if you calculate, you will get it as cn plus, if you add all this, if you perform the summation of all this, you will get it as cn plus c into n minus 1 plus c into n minus 2 plus 2c till the end of the element. Now if you take c as a common, c is a common among all these, if you remove c outside, then inside you can see that n plus n minus 1 plus n minus 2 plus, it goes on and on till it is plus 2. Now if you apply some mathematical formula, you'll get it as C of n plus 1 into n by 2 minus 1. Okay, so what is C of n plus 1? So you'll get it as n plus 1 into n by 2 minus 1. Let us say C. C will not, it's a constant, so we'll neglect C. So if you multiply this, somewhere you'll get n into n, you'll get n square plus n square by 2 plus n by 2. Okay, let us neglect minus 1. So somewhere we can see that the value is big O of n square. So the worst case time complexity is big O of n square. Now let us analyze the best case running time and the average case running time. In best case running time, we have to consider that the partition has taken place exactly in between. Suppose there are 8 elements in the array, then there are 4 sub-elements in the left sub-array and 3 elements in the right sub-array, or one element we are going to take as a pivot, which are not going to touch it, right? So, or if there are 9 elements, then there are 4 elements to the left sub-array, 4 elements to the right sub-array, and the between elements is the middle element is the pivot element. So in that case, we can say it as a quicksort is in the best case. Okay. So when can you say that quicksort is in the best case? It occurs when the partitions are evenly balanced. Okay. Suppose there are, for example, 4, 3, 6, 2, 1 and 7. So these are the elements in the array. Now let us say the middle element is the pivot element. Then all the elements in the next partition, what happens is, the next pass what happens is, we have to consider in such a way that all the elements to the left subarray are smaller than the pivot element and all the elements to the right subarray are greater than the pivot element. And the pivot element will stay exactly in between. Okay, then we can say that it is a balanced array, balanced partition. So in case of balanced partition, what happens? It is in the best case. Their sizes either are equal. So we can say that the left subarray and the right subarray are equal. In that case, the partition will be n by 2. At the most, n by 2 elements we can partition. So we can take it as n by 2. In the next level, we can see it is n by 4, because this array is again divided into 2 subarrays and the right subarray is again divided into 2 subarrays. So it will be n by 4. So this continues on. So it will be n by 8, n by 8. So once again you are going to partition. So the tree looks like this. Okay, the partition tree will look like this until the element size is 1. So the total partitioning time for all the subproblems of this size is Cn. In this particular case level, in the second level it will be Cn by 2, which is equal to Cn, and Cn by 4, which is equal to n, and everywhere it is n. Okay, with C we can neglect because it's a constant. Now what happens here is, so if it is n by, if in each partition we can commonly observe that the n by 2 partition is continued in such a way that in the next level it will be n by 2 by 2, and the next level it will be n by 2 by 2 by 2. So we can, in general, we can consider it as n by 2 power k, which is equal to 1, because finally what we get, we'll get it as 1. So n equal to 2 power k, because by using the mathematical formula we can bring 2 power k this side. So it is n equal to 2 power k, where k is equal to log n to the base 2. Right. So for log n levels are present in this particular tree. So totally how many levels are present? Log n levels are present, because the partition is made exactly in between. There is a main concept. So for each level, partition algorithm compares the elements n times. So the time complexity of quicksort is big O n log n to the base 2. This is the time complexity of the quicksort only in the best case. The same thing holds good even for the average case. Even in the average case, the time complexity is big O n log n to the base 2, because we are going to select the pivot as some random element in between, in the median or somewhere in between. Only when the partition takes place exactly, that is the size by 2, then the quicksort can be in the best case approach. Okay. So next we will go for the analysis of the quicksort, and we are going to calculate the space complexity. The space complexity of the quicksort is given as, we all know that quicksort is a recursive algorithm, and in all the recursive algorithm we know that it uses a stack, right? So the maximum size of a stack in worst case is n, right? We all know that the size of a stack in worst case is n, because n times it executes. In best case, the height of the tree is log n. So the size of a stack depends on the height of the tree. So it is big O log n in the best case, and in the worst case we all know it is n. So the stack size is equal to n. So the space complexity of the quicksort is big O of n in the worst case. Hope it is clear. So this is how we are going to calculate the time complexity and the space complexity of the quicksort. Thank you students for being with me and learning the quicksort algorithm. Thank you very much.